Okay, so guys, finally, this is the last part of chapter 4. Now, guys, I want you to recognize the importance of this part because, in fact, in the real life scenario, I don't have always a point load. What is a point load? A point load is a force located at a point. Usually, I have a distributed load all over the beam, all over the bridge, all over the gear. So I have a distributed load over my part. But in order to simplify our cases, we always want to simplify this distributed load into one point load located at a certain position. So here, guys, we will move from the cases of one point load located at a certain location to the case of a distributed load all over one part, one beam, one bridge, one mechanical part, and we will convert this into a simplified equivalent system of a force located at a point. So here, guys, I have a distributive load, could be uniform and could be non-uniform. This distributed load is always described by its intensity, omega or W. So guys, this is a very important note. So I always have that the distributive load, is described by omega or W, and this is the intensity of the load. Now, what is omega? Omega is basically the intensity of the load, and it is in fact the intensity of the force per unit meter. And this is very important note. So it could be Newton per meter or pound force per feet, per inch, whatever you have a unit for the length. So basically, guys, this omega, which is the intensity, describes the Newton per meter or the forces, the magnitude of these forces per a unit length. Let's take the example of the bridge where I have several cars. I know, guys, that this bridge here is subjected to a certain load. I can say that this load is basically 800 kilograms per meter, for example. So I have here a uniformly distributed load of 800 kilograms per meter. Now I can also have a non-uniformly distributive load like this case, for example. So in this case, guys, I have a curve that describes omega. It is not a rectangle, which means this is not a uniformly distributive load. What you should know, guys, that this representation illustrates omega, which is the intensity of the load. And remember, guys, it is never in Newton, it is in Newton per meter. Versus what? Versus x, which means versus length of this part of this beam. So I have in this representation a curve where y is Newton per meter, which means this is the intensity, and x is the length. Now, how to find what is the equivalent force of this uniformly distributive load over my beam? I know basically that the integration of this omega dx, omega is in Newton per meter and dx is meter. The integration of this omega dx is nothing but the equivalent force. So F, guys, is equal to what? F resultant should be equal to the integration of omega dx. Because in fact, guys, if I take a small dx here, and I multiply this dx by this omega, what will be the unit here? the unit is Newton, and basically this is dF. So why is it dF, or differential of the force? Because in fact it is equal to omega dx. So dF of unit Newton is equal to omega, that is the intensity at this x. Basically guys, here I don't have the same omega for each x, so this omega is varies with respect to x. So this is omega of x, omega at this x, dx. And don't forget guys, omega is in Newton per meter and dx is in meter. And this will give me what? This will give me that the force F, which is the equivalent force of all the F. I know guys that the resultant force should be equal to the sum of all the forces. Now here my forces are dF, which means F is equal to the sum of all my dF. So what does this mean? What is the sum of dF? The sum of dF is basically the integration of this dF, which means it is the integration of omega dx, because in fact dF is equal to omega dx. So guys, from here comes the equation of F resultant. F resultant is equal to integration of omega dx all over the length of this part that I'm willing to find F resultant. Now what is the integration of omega dx? Guys, remember from math that if I have a curve, the integration of this function f of x times dx will give me what? Will give me the area under this curve. I can prove this very easily, because in fact guys, what is f of x dx? If I divide the area under this curve into a differential areas dA, I know guys that each dA could be estimated as if it is a rectangle. So as if this is a rectangle, because in fact this is a very small differential area. So I can assume that it is a rectangle. And I know that the area of the rectangle is equal to this length here times this width. Now what is this length? Basically this is f of x, and what is this width? It is dx. So which means that this term here is dA. And what is the integration of dA? The integration of dA is basically A. And if I go to this special case here that illustrates the uniform, that illustrates any distributive load over a beam. So I know guys that if I divide my omega here into a small, or if I divide this area under the curve of omega into small dA, or into small differential areas, each dA should be equal to omega at this x here times this width here, which is dx. Which means guys that the integration of omega dx is nothing but the area under this curve. And from here comes this important relation that states that F resultant of a distributive load, either it is uniformly distributed or not, is nothing but the area under the curve of the intensity omega versus x. Now let's take some particular case before going to the second part where I should find the location of this F resultant. So guys, let's take this first particular case where omega is uniformly distributed over X. So what does this mean? If omega is uniformly distributed along X, and I need to plot omega versus X, omega will of course be a horizontal line. And in this case, guys, if omega is a horizontal line, and I need to find the force that is equivalent to this omega using the graphical method that states that F resultant is equal to the area under the curve of omega versus X, this means basically that F resultant here is equal to this omega here, the uniformly distributed omega, because this is omega basically, okay? So this is the length times all of this. This is the area under this curve, and this is basically L. So Fr is equal to omega times L. Omega times L will give me the area under the curve of omega. Now let's do it now in the integral method. I know, guys, that Fr should be equal to what? Fr should be equal to the integration of omega dx going from 0 to L, basically, because it is here, this omega is going from 0 to L. But I know that in this particular case, omega is constant, which means, guys, I can remove omega from this integration, and this will give me what? Omega integration from 0 to L of what? Of dx. And this is basically omega times what? What is the integration of dx from 0 to L? It is x going from 0 to L, which means L minus 0, and this is L. So you can see, guys, that if I apply the graphical method, and usually, guys, the graphical method is applied only in case of regular shapes. Because in fact, if the shape is not regular, I cannot find A. That's it. If the shape is regular, I can apply this graphical method without the use of the integration method, because I know, guys, that the integration will take somehow time, and if you didn't memorize some integration rules, so you cannot do the integration. So guys, if you have a regular shape, go for the graphical method. Then you can find the area under this curve, and this area will be F resultant. Another example, guys. Example of a triangular shape. I can find F resultant directly by finding the area under this curve, because in fact this is a regular shape. So what is the area under this curve? Now this is my curve. What is the area under this curve? It is the height that is given here by omega 1 times the base over 2. Okay, so it is omega 1 times L over 2. So this will be F resultant. And then if I know that I should locate this F resultant, what do you think? Where should be the location of this F resultant? Yes, it will be on the center of gravity of this triangle here. So this will be the location of this F resultant. And why should I worry about the location of F resultant? Because in fact, the location of F resultant will help me in finding the moment under any point on this beam. What do you think? What is the location here of F resultant? So basically, guys, the location here of F resultant is at the middle point of the beam at LV2. It is at the center of gravity of this beam.